That's good.
And we're live.
Hello, welcome back to the Astro Imaging channel, the now bi-weekly kind of bi-weekly, twice a month astrophotography show that covers everything that you need to know about how to do excellent astrophotography. I am Molly, and tonight we have with us Gary M, and he's a absolutely prolific imager. What was it? 5,000 images on Astrobin? Was that the number?
No, it's only 3.
Only 3? It
Only
feels
3.
like that. Yeah, so he's going to come on and talk about how he's imaged the entire Sharpless catalog and some of the really cool stuff that has come out of that, because it's a really, really interesting catalog that I've been picking up a lot more lately as well. Before we dive into Gary's talk, let me share my screen here of our upcoming calendar. Oh God, it has every single tab on my computer. That's just not fair. Okay, we're gonna do it this way. I'm gonna share this screen over here. There we go. All right. So this week we have Gary. So next week, it's a third Sunday, so we wouldn't be streaming anyways, but we went ahead and put on there that we're not streaming because it's Thanksgiving weekend. And then the first Sunday of December 7th, we had to postpone Mike Cranfield, who was going to talk about the Pixel Math UI, until he finishes moving. So he'll be back in February with that. But for now, it is open. Most likely, it sounds like I will give a talk on how to capture and process comets, which is pretty timely with the bazillion comets we've had through lately. We'll likely do that. And then on the 21st of December, before Christmas, we'll have Brian Kloppenberg from the AAVSO, the American Association of Variable Star Observers, come on. And we haven't quite narrowed down a topic yet, but he'll give one of his AAVSO presentations about variable stars, and likely for this channel, how you can capture them, how you can get involved in this professional amateur collaboration for doing cool citizen science. And then we'll be off the Christmas weekend, and then back January 4th with Manny Lyons giving a presentation on how you can image exoplanets. So I won't go further out than that in the calendar because you'll forget this all again anyways. But let me stop sharing here. All right. And yeah, as always, if you think of something during tonight's talk that you're like, hey, we could really use a talk about that, or I know something about that, it'd be fun to give a presentation, head to our website, theastroimagingchannel.org, and hit the contact us button and shoot us a message. And or if you know somebody, let us know about them, and we can get you scheduled to come on and give that presentation on here, because we're always looking for more presenters to come and share their knowledge of astrophotography with the whole community, with our 20,000 plus subscribers now, which is really exciting. And don't forget to like and subscribe, as they say. That helps get our videos out there more, for that more astrophotographers to learn how to do this awesome hobby. All right, so we will go ahead and dive into Gary's talk. A couple notes about Gary. He's a prolific amateur astrophotographer who's retired to Onalaska, Texas. I'm sure I'm saying that right. Took up the hobby of astrophotography almost a decade ago. Let's see. He does he images all kinds of stuff all over the sky. He's published 8 books in astrophotography, 12,000 hours on 2,500 different DSOs. Those numbers might be slightly out of date. Tonight's talk should be a lot of fun. All right, take it away, Gary.
Well, thanks, Molly. It's always a pleasure to be here. This is my 5th fall to be here, and I'm honored to be back. It's always a thrill to talk about the work that I've done. In this hobby, you don't get a ton of feedback, so it's really nice to hear, especially through the questions and comments, some of the feedback. It's really appreciated. So I'm going to start my talk now, Molly, and help me out, make sure that I'm doing this correctly. So I'm going to share my entire screen.
Yes.
And see if I can get it pulled up here. So let's see. So can you see that?
Yeah, I mean, you can hit that hide button on that bar at the
bottom.
bottom.
That's right. Hit the hide button. Yeah. There you go.
Yeah, that looks good.
Great. Okay, so welcome everybody. I appreciate all of you who took the time on your Sunday night to be here with me to hear about the Sharpless Catalog. And I'm going to go through and talk about what the catalog is, some of the history behind the catalog, the author of the catalog, go through some of my favorite parts about the catalog and how I've imaged them, and then I'm going to conclude with a bit of science, I think. It's something that I don't think any of you have seen before, and came too late to put in my book, but it's some really interesting stuff I want to share with you and see if you, some of you can help me figure out what I'm seeing when I look at this. So let's dive right in. I've got a lot of content today. We're going to try to keep it to about an hour. As I've talked about, this is really the accompanying presentation to the book I published about a month ago. It's available on Amazon. It's the 8th book. I've imaged the complete Sharpless and Messier and ARP and Hickson and VDB catalogs. Caldwell, I did as much as I could. So all of this is from my backyard. I live in East Texas. So Caldwell, as most of you know, is objects that are all over the sky. So I was only able to get 85 of those. So that Messier book has some of the highlights from Caldwell, but I can't get the whole Caldwell until I decide to visit South America. And you can see my other books there as well. The proceeds from all of those books go to a scholarship fund that I've set up, and some of you have helped donate to, which goes awards each June to college students that are majoring in one of the sciences and have a future career in astronomy. It's been a great hobby for me to be involved with. It's been very rewarding, and it's just nice to be able to give back a little bit in that manner. So these are a couple of pages. This is the book. Well, I'm not going to hold it up because you can't really see me very well on the tiny screen, but there's nothing to see anyway. It's just a book. It's about 150 pages, and this shows you just a couple of pages. Basically, there's a lot of different content in the book. There's a catalog, there's a table at the back and an introduction, but most of the book is simply the images of each of the 313 objects, examples of which you can see here. And then obviously I provided a description of each object, how to find them in terms of location, the nicknames, the rating of the object from 0 to 5 stars. We'll talk about that in a little bit. The palette that I use, which I think it may not be the best palette, but it's what I thought at the time anyway was the best palette. We'll talk about how that changes as the gear and the processing that people have improve over time. And then some other data about the objects, like the distance away and the width of the object, which is important when you're trying to frame it and stuff like that. So I've tried to, as an astrophotographer, I've tried to provide you with all the information there that I think you need if you want to go about trying to image these objects on your own, which I definitely would encourage you to do that. So let's talk a little bit about the background here to the Sharpless catalog. So Dr. Stewart Sharpless was born in Milwaukee in 1926. I was born in Milwaukee. And actually, Dr. Sharpless looks a little bit like my grandfather. So I don't know if I'm related to him. I'd like to think I was. But he completed his dissertation at Yerkes Observatory there, and I think it's near Lake Geneva, Wisconsin, in '52, and is awarded his PhD by University of Chicago. And I will say this about Dr. Sharpless: he is, of all of the people that I've done research on in this hobby, he is the most reclusive. I could only find a single picture of the man, and this is it. He's had a career of 50 years, and I can only find one picture of him, and very little information, especially about his personal life. So it's really interesting. He's famous for some of the work he did in the 50s, and then he stayed, as you'll see, he stayed at an observatory until the end of his career, but really not a lot of information about him that's out there, which is great. I think he just loved his hobby and didn't really care, didn't have social media, didn't care to put anything out there, so that's fine. Now, he worked for an amazingly short time. He's famous for his work at Palomar Observatory, but he only worked there a very short time, one year, as I understand it, or less, under a Carnegie fellowship. And that's where he published his first Sharpless paper in 1953. And that was called A Catalog of Emission Nebula Near the Galactic Plane. And that had 142 objects, less than half. And all the paper says is that he used the 48-inch plates from Doctors Abadi and Mikulski. I think these are probably the same plates that were the start of the PAS-1 survey, which we'll talk about here in a second. I think they're the same plates, but it doesn't say that in the paper. So anyway, he published that paper in 1953, then accepted an appointment at the Naval Observatory in Washington, D.C., and studied H2 regions in the Milky Way galaxy for about 10 years. And then during that time, he published his second paper, and that's the one that we all know and love, and that's why we call it SH2, because it's his second paper. And that's called A Catalog of H2 Regions, and that has what we now know as the 313 objects. And this paper used the Palomar Sky Atlas plates, which we'll talk about here on the next slide, which is referred to as PAS 1, which stands for Palomar Observatory Sky Survey. And they always put an I there for 1 and a double I Roman numeral for 2. So that's the nomenclature that I've used. Now, in 1964, he became director of, at that time, the New Muse Observatory in Rochester, and that's where he stayed for the rest of his career. And he continued to work at that observatory. And his obituary, it says, after retiring from the university, he stayed in Rochester and devoted himself helping children and youth with emotional behavioral challenges. I believe he had 2 sons, but that's the only information I could find about him. He died in 2013. And this information is not really important for you to know, but I just find that, whoever we're talking about here, it's always nice to just find out some background on these folks. They weren't people that tried to make a name for themselves in terms of being famous or being rich. They just did some great work, and we benefit from that work that they did in the hobby that all of us enjoy at this time. So let's talk a little bit about that POS-1 survey. It was the first comprehensive survey of the sky, and it occurred at what at the time it was just called the 48-inch Palomar Schmidt telescope. Now it's called the Samuel Oskin telescope. It was renamed in 1986. But this telescope that they used is a Palomar Schmidt telescope specific for photography, and it was completed in 1948 as the largest Schmidt telescope in the world. And you can see here, so the lady that you see here is Jean Miller, the astronomer you see here, and she was actually involved in POS-2, which was kind of in the 1990s timeframe. And so they used this telescope to take about 2,000 plates. About half were, exactly half were red, half were blue. And it's important in the sense we'll keep coming back to this POS-1 survey. It's important for a number of reasons, but this is the information that Dr. Sharpless used for the formation of his catalog. So let's talk about the catalog in a little bit more detail. So he established the catalog of H2 regions, like we said, in 1953. He was the lone author of both of those, and he said the purpose of that catalog was to serve as a finding list for radio and optical astronomers, as well as a source of diameters and descriptions of H2 objects. I don't think he ever dreamed that this would be a benchmark for astrophotography about 60 years later. But that's the way it's evolved. Now, the catalog is interesting how he identified the objects in his catalog. He wasn't applying, as far as I understand, and keep in mind, I am not an expert in this field. I am just an amateur astrophotographer that did some research. And so I could be wrong about some of this. This is just what I found in my research. But he did not use science per se in identifying objects in his catalog. He was simply looking at these POS-1 red and blue plates to determine, well, where are the nebula? What should I be including in this catalog? And we're going to go through some of those plates and take a look at them. And I want you to, put yourselves in the shoes of Dr. Sharpless and try to pretend what it was like to actually take a look at these plates and try to determine, is this an object that we should include in the catalog? He tried to exclude planetary and reflection nebula by visual inspection, and we'll talk about that here in a second. But as you'll be able to see here, some of those slip through. And as it currently stands, his 313 objects for the Sharpless catalog includes a whole lot of objects in addition to simply emission nebula. In the second paper, he started using the term H2 region instead of emission nebula because, like I say here, he said that the H2 region is an entity defined not only in terms of the ionized gas, but also in terms of the hot stars, which are responsible for the ionization. So part of his work in these papers was also not just identifying the nebula, but identifying the stars which are energizing these objects. But he was only able to do that for about half the objects in his catalog. In terms of what's in the catalog, and it's interesting, this wording is tricky, so I want to be careful how I say it. So the catalog consists of the entire sky north of a declination of -27. So it includes everything north of that. But the way the coverage was, if you look at, I've got some maps that show the coverage for the POS-1 survey. it wasn't complete. And so he does include 18 objects that are south of minus 27. So it goes from minus 27 to minus 40. And I say here, note there's currently over 8,000 H2 regions that have been identified in the Milky Way. So he included his 313 he wanted to pick. Obviously, he didn't see all these 8,000. Some of them didn't show up on the sky plates he had at the time, just too dim or too small. But he tried to pick, the 313 that he saw on these plates. Now, if you want to try to image this catalog, you have to be able to get down to minus 40, because you'll see there's a few objects that go that far south. Now, we do refer to this catalog as the SH2 catalog because it's the second paper that Sharpless wrote. And we refer to these objects as SH21, SH22, up to SH2313. Now, there are several interesting objects in this first paper, SH1, that he discovered were not H2 objects, and so he did not include them in the second paper, but they are some really interesting objects. SH189 is the most interesting one of those that are in there. But if you're looking for kind of obscure objects to image, it's fun to go through those objects that he had initially identified as bright enough to be included as SH1, but then later drops. And these are typically planetary nebula that were dropped out. SH189, I believe, is that. So this shows you the breakdown of the 313 objects. Now, 265 are emission nebula, like we talked about, but there's 16 planetary nebula, there's 13 molecular clouds, there's 9 supernova remnants, 6 reflection nebula, 2 galaxies, and 2 missing objects. So let's just focus on the emission nebula right now. So there's 265 of those. And what I'm showing here at the bottom is that in my images in the book, I tried to break that down because as an astrophotographer, we approach these emission nebula in different ways depending on the composition of the emission nebula. So for many of them, they are really dominated by hydrogen. You might be able to find some oxygen, sulfur in there somewhere, but it's hard to make a good image, at least in my experience. It's hard to make a good image when the H2 is just simply so dominant. And so the majority of the images in this book are primarily images where I've taken RGB subs and I've added H2 to that and blended them in. Most of the time I use PixInsight. Most of the time I use the narrowband combination process that they have there to do that. But you will see most of those images are primarily red because hydrogen is assigned to the red channel. Now, I prefer actually to do full narrowband. And so 37 of these objects had enough of and by the way, in the compendium that I wrote, I try to break down this ratio of H2 to O2 to O3 to S2 so that you can see, because typically if there's less than kind of the 10% of the signal in terms of the relative ratio of oxygen or sulfur to hydrogen, if that gets to be too low, it's really hard to make a good full narrowband out of those 3 channels. But in the book, I did full narrowband for about 37, and I did 3 of those. In addition, 3 of those are Stragran spheres, which includes like the Rosette Nebula, and so I did those that show full narrowband as well. And then 6 were Wolf-Rayet, and those are, we'll talk about those. Those are fascinating, very strong, very massive stars that emit tremendous emissions. And so those end up being some of the prettiest nebula that we know about, like the Crescent Nebula or like Thor's Helmet. And those, in my experience, are best with just a simple bicolor combination of the HOO. And so obviously when you're processing these individual Sharpless objects, you can pick whatever palette you want. I'm just telling you what I found through experimentation to be the best on each of these objects that I used. Now, I will say, as time goes on, and I'm doing this right now, I'm going back to some of these Sharpless objects and re-imaging them. And some of the objects which I thought we didn't have enough oxygen and sulfur, well, now with the faster scopes we have and with the processing tools we have, we can start making full narrowband images out of some of these images that I thought before we didn't quite have enough signal to do that. All of the time, we'll talk about this in a minute too, but all of the time, maybe not all the time, most of the time, I am actually processing starless images when I stretch the nebula, because otherwise if you stretch it with the stars in, as most of you know, the stars become quite messy. So I try to separate the stars and the nebula and stretch the nebula a little bit harder than the stars. And I'm going to take questions here in a second, but I do want to say a couple of things. So first of all, there's a question here about why are objects included in the Sharpless catalog that are not emission nebula? Now he had the plates, and so at first glance you're saying to yourself, well, it's easy to tell the difference between, let's say, a planetary nebula and emission nebula, or it's, you know, how can you confuse a galaxy with an emission nebula? So I want to show you how that happened and why that happened, and then I want to move on to these missing objects, which is a bit bizarre. How do we have missing objects? Dr. Sharpless looked at these in 2 different papers. He looked at the objects for the first paper. So these missing objects appeared in both papers. And so what happened to them? Why are they missing? Why can't we find them? And that's what we're going to talk about towards the end of so I've done a lot of work on that after I published the book, and I've got some interesting things to show you, which I think are hopefully will spur some good conversation. So before I do that, is there any questions, Molly? Is there anything that's come up that we should address?
We haven't gotten any questions yet, Gary. There was a suggestion from Jim. Well, it wasn't a suggestion. He just said that he kind of hopes you stop publishing soon because he's already spent a ton on all those books. So I cannot second the motion that you stop publishing, but perhaps you should try maybe some other longer catalog like the NGC or something like that. That way it'll give us time to rebuild the bank account. But there are no other questions.
Okay.
Oh,
Actually, Gary,
there is one. It just came in. What is the overlap, Marcia wants to know, between SH1 and SH2?
Yeah, I don't have the numbers on that, unfortunately. I wish I did off the top of my head. So I don't know. Basically, basically the main difference between SH1 and SH2 is he just added a ton more, and part of that's because at this same time, so he published that in 1953, and they were doing those PAS1 plates from 49 up to 58. So they were still doing the plates. So they were still coming. So he didn't issue that second one until the PAS1 survey was finished. So I'm sure there were some additional plates that he had out of those 2000 that came in, and he was able to get. So the main difference is you got additional objects. So basically he took, I'm just going to use these numbers roughly, you know, he probably took 90% of what he had initially of those 142 and moved them forward with a bunch of others to get to 313. But there were a few in that first survey that he dropped out because he was able to figure out in the meantime that they were not emission nebula. And I don't have the information to know how he...
So Sharpless 1 is a cleaned up subset of Sharpless 2.
It's no, I mean, Sharpless 1 was his first
right
estimate.
But what most of the objects that are in Sharpless 1 came back in Sharpless 2.
Yes. It was only those that he figured out, and I'd be really intrigued to find out, you know, exactly how he did that, what came to light in that time. But you know, there's so much of that kind of stuff I have questions about. I'm never gonna figure out. Okay, well, let's
just a second. There's a couple of questions coming in as we speak, and I think you said that you're going to talk about the missing objects later. So I think defer a couple of these.
Yeah, I mean, this is
and what about NGC 1232? Is that in the Sharpless 2 or 1?
I don't know that off the top of my head. It doesn't sound familiar.
Okay, Scrappy Dappy Doo. I'm not talking to you, Gary. I'm talking to Scrappy Dappy Doo, the guy who wrote that last comment. Maybe you could fill out what you're talking about, little at the bottom. Fill it out in chat, and by the time we get to the next question break, we'll be able to ask Gary better. Okay? So we are through with questions for now. Gary, take us back to the Sharpless.
Okay, so I want you to pretend like you're Dr. Sharpless or one of his assistants. I don't know exactly how this worked. You know, he probably did a lot of this work himself. Now, so these are the original plates. They're not the original plates, and that's important for our talk later. They're copies of the original plates. The original plates are archived somewhere in Palomar Observatory, and somebody needs to get after that because it's really important that we see what those original plates are. You'll see why later. But they made copies of those plates. And so for the most part, the copies are fine. You know, they're not really that much different, but there's an important reason how it is different. I'll talk about that later. Now, I was just going to show you what the plates look like, but I ended up having to lighten them up a bit because I was afraid when they came to you across the vast internet here, you wouldn't be able to see some of the subtle variations. So these are a little bit stretched, just a little bit, just to hopefully give you some of the variation of what you can see on the screen. Now this, what I'm showing you here, this is an object, and you can see on the left is the POS1 red plate. On the right is the blue plate. And typically the signal is going to come across, obviously, on the red plate. But for these bright nebula, and this one has a brightness of 2. So I'll talk about this here in a minute. Each of these objects are rated 1, 2, or 3. So this is a kind of a medium brightness one. And you can see on the left, you can see some signal there. You can even see a little bit of signal in the middle one. And so most of you probably recognize this one here. And so for each of these, I'm going to show you what the plates are, and then I'm going to show you my image. Now, what you'll see as we go through this is that even though they used the 42-inch scope, 48-inch scope, and they used, 1 hour exposures nominally, we can still get better images today from our backyards, which is pretty amazing. I like that. Not only that, but we can get color images, and that helps in some ways, as you'll see later, because sometimes it's hard to tell the balance of the red and blue when you're looking at these images. But this just gives you a feel for what Dr. Sharpless saw, and then what the object actually looks like. So that's for a bright nebula. That's easy. So let's go to a dimmer example. This is a nebula that has a brightness of 1, and which is the lowest level. And I'm not sure if it comes across well, Alex and Molly, but this left one, the red one, it's got a very faint signal at the center here. It's very dim, and it just looks, it's really hard to see, but it does show up, and not much shows up on the blue. Now, when Dr. Sharpless was looking at these, they often would not look at this. They would look at the inverse of this, and that's what this looks like. So this is an inverse of the plates that Dr. Sharpless was looking at. And again, hopefully you can see on the left here in the center, there is just this faint amount of nebula here. And on the right side, you don't see anything. Typically, these faint nebula would not show up on the blue plates. They would just show up on the red. But my point in showing you the plates themselves is that it's not that easy to see these nebula. Now, this is what the nebula is. It's SH2253, which is fairly dim nebula, although you can see from my image. So my images, by the way, I haven't really stretched my images all of that much. I don't overstretch them. I try to show them if they're gonna. I want faint nebula to still show up as fairly faint. If you wanted to, in PixInsight or whatever tool you use, you could stretch them and they could be bright. But I like it. So in my book, you'll see, relatively speaking, the faint ones are faint, the bright ones are bright. So I did stretch this right one a little bit, so you can see it. But it's much easier to see in my image than it would be on either of the sky plates. But you can still see it in the sky plate. So let's go on to another one. And this is another example that's a dim one. And you can see, again, we have the red and blue plates here. And I'm going to show you the inverse. So this is what the inverse looks like. So now on the left, hopefully you can see in the center here, there's a very faint nebula coming through. You'll always see the stars, of course, but you see a little bit of black behind those stars. And on the right, you actually see a faint signal as well. So some of you may know what this is just based on that unique star pattern there. But this is actually a planetary nebula, and it's SH200. So my point in showing you this, on the surface, it's like, well, why did Dr. Sharpless put planetary nebula in his catalog? Well, he doesn't have a special sign that says this is a planetary nebula. He has to inspect these plates. And you can see from these plates that I actually see more signal on the red side than I do on the blue side. Although when you combine them, it actually looks like, you see more of the blue signal there. but of course I'm using narrowband as well. So I'm able to bring out, he wasn't using narrowband. So he had to base his observations just simply looking at these plates. And he thought, as I would too, that this was simply an H2 nebula based on what he saw, or an emission nebula at least. So that shows you an example of what a planetary nebula looks like. Now, this is another really dim example. And if you look at the center here, you can see there's another faint area. I'm going to move to the inverse here so you can see this. So now here you see on the left side, we do see some faint signal, but on the right, you see another fair amount of signal that doesn't approach the red signal, but it's pretty strong for a blue plate. And what this object is actually a molecular cloud. So you can see these molecular clouds are typically very faint. They're whitish. They're away from the plane of the galaxy, and they're basically reflecting the light, the broader light, not individual stars like you see in a reflection nebula, but the broader light. And in this case, you can see why he would probably mistake that as an emission nebula. Now, I say mistake, there is some emissions in this molecular cloud, but it's not something that I would have thrown in with the rest of his emission objects, for example. But that's another example of how a molecular cloud is going to show up on these plates, somewhat similar to an emission nebula. And then finally, I want to show you this one here. And this is one of the more interesting ones. You can see in the center here, we've got faint signal. On the right, we don't have anything. I'm going to show you the inverse now. And this is actually one of the galaxies. So this is Maffei 2. I'm not sure I'm saying that right. So I think SH2 191 is Maffei 1 and SH2 187 is Maffei 2. And those are these elliptical galaxies that are very faint, kind of reddish when you image them. And but on the plates, if you look carefully at the plates, they do look like emission nebula. I think the fact that it has a bit of a core there kind of gives it away that perhaps it's not, but there's emission nebula that look like that. So you can certainly see how he may have mistaken that for an emission nebula as well. So that's all I'm going to show you in terms of that, but I just want to show you how Dr. Sharpless, when he was looking and developing his catalog, it wasn't that easy just to say, well, this was an emission nebula and this is a galaxy, or this is an emission nebula and this is a planetary nebula. He had to do it by visual inspection, and sometimes he was going to make mistakes on that. Not really any fault of his, but it's just hard. If you're just looking at the plates and that's all you're doing, it's hard to know. It's hard to make that judgment. So any other questions, Molly, before I launch into the content of the Sharpless catalog?
No, I don't think there's been any new questions come up.
Okay.
So you're good to go.
Okay, great. So let's talk about the catalog itself. It covers a wide range. You can't really just use one setup or one approach to do all of these. So the size ranges from 0.7 arc minutes, which is very, very tiny. I mean, just to give you a feel for those of you that may not be familiar, the moon is about 30 arc minutes. So 0.7, and that's 1/50th of the moon or something like that. It's not very big, and that's what this object on the left, which is a planetary nebula, SH2 179, that's the smallest Sharpless object. And then the largest, it's not here, it's 1500 arc minutes. The largest is something called the Fishhook Nebula, which I didn't even want to show that picture because I had to, well, for all of these really large ones, I could not use my telescope setups. I had to use my DSLR because when you talk about 1500 arc minutes, for example, in terms of degrees, you're talking about something that's 25 degrees or so, if I can get the math right there. I think that's about right. So, that's a lot. You can't have a telescope set up for that big. Now, this one on the lower right is about 1,000 arc minutes wide. This is SH2 109, and that's an interesting one because it basically covers the big objects in Cygnus. So you'll see in here, if you look carefully, you'll see this is the butterfly there and around the solder. This is the North American Nebula up here, and this is the Crescent Nebula. So if you want to image the Sharpless catalog, you've got to have setups that can do very broad images, but also very tight ones. And similarly, the actual sizes of the nebula range from very small, 0.1 light year, which is what this planetary nebula is, all the way up to 1,500 light years. The distances range from very close, 360 light years in terms of, cosmic parameters of astrophotography, 360 to 33,000. And the declinations, as we've talked about before, range all the way from near the North Pole all the way down to minus 39. The most common constellation for Sharpless objects is Cassiopeia with 43 objects, and I could probably win a bet by asking you how many constellations do these objects appear in, because there's 88 constellations total. So, you know, the Sharpless covers a big part of the sky. So I'll let you think about that. How many constellations, I'll show you the answer here in a second, but how many constellations do these objects show up in? In terms of the breakdown of how, let's say, just quote how good these objects are, this kind of shows you the scores that I from my compendium where I rate each object in the sky. And you can see there's quite a few showcase objects. 20 out of these 313, there's 21 showcase objects and 46 that are excellent. So that's a total of almost 70 objects that are really good objects to image. There's 51 that are good. And then, you know, 100 that are so-so. There's 83 that I say only for hardcore imagers. And then there's a few that I call not worth imaging. But the Sharpless catalog has a lot of objects that are fun to image. And that leads to the question, well, is Sharpless the best catalog for imaging? It's kind of a stupid question because, you know, you don't have to stick to one catalog. But if you were on a desert island and you had one telescope and you had to pick one catalog, I think Sharpless would be the choice because, you know, I didn't include all the catalogs here. I just compared Messier and Caldwell on Sharpless. But first of all, you've got, you know, 3 times the number of objects. The big difference, though, is these lines here. So the Sharpless is very short, as you'd expect on galaxies. So that would be the big bummer about sticking with Sharpless, is you don't get any of these fantastic galaxies to image. You also don't get any star clusters to image. And you know, for those of you that have imaged the Messier catalog or the Caldwell catalog, you know that it's a bit of a slog to get through all of the clusters. It's not visually, you know, through the eyepiece they're pretty, but imaging, I grew to like imaging clusters, but still, it's not as exciting. I can tell you, when I imaged Messier and Caldwell, I started getting tired of it at the end because of the repetitiveness of the clusters, particularly. But the Sharpless, all the way through, I mean, it was a little bit of a drag at the end, but the nebula were always interesting. You can see, though, when you compare, especially the full narrowband nebula, you've got 46 Sharpless ones, and you only have 4 in the Messier catalog and 7 in the Caldwell. And, you know, supernova remnants, which are a blast to image, you've got 9 of those in Sharpless. And so there's just a lot more, I think, for an astrophotographer. There's a lot more meat in the Sharpless catalog. But, of course, you know, the advantage of Messier and Caldwell, you've got some fantastic galaxies there. In terms of location of the Sharpless objects, this gives you a map, a visual map. If you look at the Milky Way, so on the horizontal axis is right ascension, which is a proxy for the transit date, which I have both of them there. And then we've got declination here. 0's the solid horizontal line, and then it goes positive to 90 and then down to minus 50. So it shows you all 313 objects, and basically you can see they pretty much track exactly along a line that maps our Milky Way, which is what you expect since they're all in our Milky Way. You don't see too many. If I'd show you a galaxy map, they would be exactly opposite. You'd see all the galaxies on the outside. A couple of notes here. So the Sharpless objects are numbered in order, and this is the way he did his original paper in 1953, in the order of galactic coordinates. Which basically follows, it starts here, you see 1 here, but it starts here and it follows the Milky Way up and all the way around from left and then going to the right. So it's not exactly, if you look at the numbers, it's not exactly, the right ascension is not exactly in order, but it's close. And you can see, you know, like here you've got 1 and then 2 and 3, 4, 5. So, you know, kind of skips around a little bit. So it's not quite in order right ascension, but it's pretty close to that in terms of how he's ordered it. A couple of notes here. The first 35 entries, which are these down here, are all off a little bit. It's not going to affect you too much. You'll probably still see it. It might affect you if you don't check it, though. So you can't just, for those first objects, you can't just blindly put the coordinates in and expect it to be centered very well. And those were off because at the time when Sharpless was coming up with his nebula coordinates, he was mapping them all to nearby stars, and the star dates he used for the coordinate systems were a little bit off. I think he was assuming they were from like 1870 and they were from 1850 or something like that in terms of the coordinates. So he ended up calculating the wrong positions for that. And even today, in things like Astrobin and Aladdin, you might see that same error on some of those, and that all dates back to the original error he made. Now, that error was only in the second paper. It wasn't in the first one. The first one, he just did galactic coordinates, which were fine. But when he converted those to right ascension, in the second paper is when he had the problem. And then, as I say here, so Sharpless objects only occur in 29 of the 88 constellations. So that's less than a third. Well, it's about 1/3 of the constellation. So that surprised me, and it's because obviously they map along the axis of the Milky Way. They're not spread all over the map here. So in terms of imaging these objects, all of the images were obtained from my backyard, and this shows you a picture of where I live here in Onalaska, Texas. So I live on a shore of a lake, which is 8 miles to the south side. You think that would be a perfect setup for astrophotography, which it is, and you think I'd plan it that way, which it wasn't. My wife just loved the house on the lake, and we loved to fish. And I didn't pick up astrophotography until after we moved here. So it's just very, very blessed to have a site that looks out over the southern sky. I took these images mainly with 2 setups. My RASA, which is the wide angle one, which is great for these Sharpless objects, is f2.2, and then my Edge HD for some of the long focal length for the small objects. And as I say here, the light gathering of the RASA was convenient for the fainter nebula. Cameras were all EWO CMOS cameras, which I'm sure you're familiar with. I particularly love the 6200, which I have now on both of mine. It's an expensive camera, but low noise, and it works out so well. And then, as some of you know, my integration time for the Edge HD is 5 hours. For RASA is about 2 hours, and it's just something I stick with. And the advantage of that really is it gives you a good feel. If I had mixed in like 100-hour with a 3-hour, and the 100-hour looks great, and you image it and doesn't look great, you may think, well, what's up with that? But it's the book is pretty consistent. So the objects that maybe don't have as much detail, don't look as great, they maybe would look better if I imaged it for 100 hours instead of 5 hours. But that wasn't what I decided to do, and I'll come back to those objects, at a later time and add more hours. But my initial pass through the catalog here, which is 313 objects, I didn't want to spend 100 hours on each one because it would have taken a little while to get through the catalog. As a tool for finding these objects where they were in the sky, I used the compendium that I put together. Most of you are familiar with this. It's a free download. You can find it in various places, Astrobin on my website. It runs on Excel. It tells you where every object in the sky is at every moment. You just put your location in, and it'll tell you what the best ones are to image at that time. And it's got all the different catalogs and all the data. And so that's what I used to find where these objects were in the sky. And then to process them, I use primarily PixInsight, but I also use Photoshop occasionally and Lightroom once in a while. So for example, Lightroom has got the best masking capability of anything. So if you ever want to do some touch-up work on some of these, Lightroom's a nice tool to use. And it's also nice to store your images and to keep them there in a database. As I said before, the nebula were pretty much all processed starless with the stars removed and then added later after I stretched the nebula. I didn't try to overstretch these nebula too much, but I don't like having messy stars. And, it's just my personal preference that I would prefer to remove those stars and have them look a little more orderly. The RASA, because of the way the wires are and the way the mirror it's all set up, you do end up with kind of messy stars if you stretch them too much. I tried to show the objects in the books are all shown consistently so that vertical north is up and east is left, which is kind of what we're used to seeing in some of the Sky Atlas programs, so that you could help you with the framing. And as I said, the stretching is consistent throughout the book. And all of what you see in the book is available on Astrobin, so you can download the image and then see all the equipment that I use in terms of the filters and the exposure time. So now, part of the catalog, and when you have the book, you'll see this, Sharpless rated each object in 3 categories: form, structure, and brightness. And I put those in the table and in the description. And let me just cover those briefly. So form, I think of that as shape. So we categorize one of the first of these 3 is the shape of the object. So one would be more of a circular object, and you can see that example here. And he did that out of the 313 objects, the circular one comes up about 58 times. Elliptical is a 2 in that column, and that would be about 51 times. And most of the objects in the Sharpless catalog are what they call irregular. So you can see here, they're not really circular or elliptical, they just got to have an odd shape, and that's the majority of the objects. So that is the first parameter called form, which I think of as shape. And the second one is called structure, which I think of as like the texture of the object. And so the easiest one to think of is 3. That's the filamentary. So that would be, obviously, Crab Nebula is a good example. That's where you have a lot of these arcs and bright, a lot of what I call texture, a lot of interesting, that's what you want to see when you're imaging the object, is some texture and some things that make it visually interesting. On the other end of the spectrum is amorphous, which is simply like a blob. It's simply like a plain, almost like they colored it in with a solid color. And some of them are like that, 68 of them are like that. By far, though, the middle category is where most of them are, and that's a hybrid. It's not quite filamentary, but it's not amorphous either. It's got some, what I call, texture. So that's the structure part. And then the last one's brightness, and that's pretty obvious. So you've got like these molecular clouds, which this is one that'd be faint. There's 87 of those, and then there are some that are very bright, and then the majority, again, are medium. So I show those parameters, but I can tell you, I've spent over 5 years imaging this catalog, and these parameters, I thought they would be really useful for me, but I didn't really use them for much of anything. I'm putting them in there because Sharpless, put them down, but I'm not sure you'd ever want to sort and find out, which ones were filamentary or not. But, that's in there if you want to use the data for that. But let me just say I didn't find that particularly useful. So I'm going to talk about the highlights of the Sharpless catalog, and I'm going to move through this pretty quick. Before I do that, are any questions, Alex, that we should take?
Yeah, we've got, Eli wants to know if the compendium itself has been updated to include all the Sharpless targets.
Yeah, I've got over 3,000 objects in the compendium, so it has all the Sharpless, it has all the VDB, it has all the ARP, it has pretty much all of everything. And what it doesn't have every NGC object. Any catalog that has, let's say, more than 500 objects, I wasn't going to put those in there. And the reason is because that compendium has got over 3,000 lines of code, over 3,000 images, and over 300,000 lines of data, pieces of data. And so it started to bog down. I used to have more objects in there, and I had to take them out because Excel just was getting bogged down and starting to crash. So it was more a limit of what I thought would be useful to people. And the other thing is, just sorting through a spreadsheet that has that many objects is kind of a pain. Now, you can do filters all you want, as you know, with Excel. But to answer the question, yeah, all of those objects are in there.
Okay. And I suppose at some point later on in the show, you will be telling us how one can look into the compendium if there are people out there who haven't met the compendium yet.
Probably not.
Yeah, there probably aren't anybody who has.
Probably not. I mean, yeah.
There's a fella.
They can find. You can find it. It's not. And there's actually another. So you recorded I've got 2 talks actually on the Astrophotographers Imaging channel. So you can go back to those talks on the compendium.
Yeah, we've had.
I've just got too many other things to cover here, Alex. That's all.
Alex wants to know. That's me. What's a Strontian nebula?
Yeah. Obviously I looked that one up, but I wouldn't be able to tell you off the top of my head. I wouldn't be able to give you a good explanation of that without bordering on telling you falsehoods here. It's just a different type of emission. It's a stronger emission, but I wouldn't.
Okay.
You're probably best asking Mr. AI to do that for you. By the way, I think my book is probably one of the last non-AI things out there. Maybe, I don't know. Could be.
Okay, and remember the question about NGC 1232?
Yeah,
I checked it out for you. It's not a Sharpless object, so if anybody knows about it, go ahead and chat, and you can tell Scrappy Dappy what you know about 1232. But I don't think it's going to be part of the show tonight.
Okay.
So, having said that,
okay, let me move on here. So I'm just going to go through this pretty quickly. So, my top 10 Sharpless objects, they're pretty cool. So let's go through them. SH2308, and everybody's got their criteria, what's best. For me, I like things that are visually exciting, different colors especially with full narrowband. Now, these first two are not full narrowband. These first two are Wolf-Rayet Nebula, which are these massive stars that create these fantastic patterns. You know, and you'll see these called as a planetary nebula by some people, but obviously they're way too big. It's just simply a star that's energizing vast amounts of emissions here. And typically they'll have a pretty big oxygen part of it. That makes them exciting. Eighth is the Trifid M20, which obviously is beautiful, but really that's, I mean, that is a Sharpless object, but it's funny because only about half these objects are what you call full narrowband. This one is kind of an RGB with some hydrogen added. Seagull, which is one of my favorites, and that actually is comprised of a number of different Sharpless objects. Number 6 is the Heart, which obviously what is it, Malap 20, the center of that heart is just fantastic. I just love that object. Rosette Nebula, which is Stravian Sphere, as we talked about. Supernova Remnant, which is Crab. Another big supernova remnant, which is Cygnus Loop. Orion, of course, which is a beautiful one. And of course, my favorite is the Eagle. Now, this is just the center of the Eagle, but yeah, no matter what part you show of the Eagle Nebula, it's going to be fantastic. So those are my top 10, and those are the ones I show on the cover of the book. But let's talk about something that I think is more interesting. That's the most underrated objects here. So these are ones that you may not see as much of, but I think they're still fun anyway. This is SH241, and this is it's in one of the big star fields there. I can't remember if it's Sagittarius or what it is in southern sky, but you've got some great dark nebula. You've got a really good field of emission, and you've got some clusters. And to me, the whole thing is just really a lot of fun to image. And I think it actually is centered. It's centered around the Messier object here, which is the only Messier star cloud. I can't remember if that's M24 or what that is, but it's just a beautiful composition. So SH241 encompasses all of that, and I think it's really a nice one. You're seeing this one more and more. This used to be not imaged very much, SH2-112, which I call the Hermit Crab Nebula. If you look at it upside down, it looks like a hermit crab. But it does have a fair amount of sulfur and oxygen. Actually, it's more just sulfur and hydrogen, but it just makes for an interesting combination. SH2301, same thing. You're seeing more and more of these lately as people get faster scopes, because it's really a pretty one. It's got a lot of oxygen in the center, and you can create some nice views of that. The Planetary Nebula, SH271, you've probably seen that around, and that's got a lot of nice texture and some nice arcs there from typically you've got the hydrogen on the outside, oxygen on the inside for a Planetary Nebula, but it's got a lot of nice structure and texture. And then SH2-284, which again, it's got the pillars like you'd have with the Elephant Trunk Nebula. It's got some nice emission areas. It has the nice dust clouds, dust lines going through the features. And so it is a relatively unknown one, but you're seeing more and more people image that. So what about the other emission nebula in the sky? We talked about there's 313 in the catalog, but there's 8,000 in the sky. So what's up with that? I mean, why did Dr. Sharpless, why did he stop at 313? Well, I can't answer that one, but I'll show you a few that I think he probably should have included instead of the ones that some of the ones he did. So I think probably the best one that is left out, and this is maybe, we can debate, I guess, those of you that may know others, but I think it's what we call the Propeller Nebula. And you can see how it shows up on the POS-1 plate. I'm not exactly sure why he wouldn't pick this as something that would be a nebula to put in his catalog. I'd love to talk to him about that. But I find that to be an interesting, not only that interesting for an H2 perspective, but it's also good for a full, this is showing you the full narrowband on the right. And then there's others out there that didn't make the cut either, and you'll recognize a number of these. Barnard 35, this is what they call the Angel Nebula, as NGC 2170. And then these bottom two, which you're seeing, actually somewhat faint, but you're seeing more and more. And in fact, I'm doing a full narrowband on this lower left one right now, LBN 380, because it's got some of these nice features, these arc kind of features. And so that gives you a feel for the fact that there are nebula out there that are not part of the Sharpless catalog, but are still really interesting nebula to image. So now what about the missing objects? I know Yui asked about that. And this is not in the book, unfortunately, because this is just something I've been losing sleep over for the last month. And so I've developed a lot of respect for the work Dr. Sharpless did. And to say that that he spent all the effort to put them in two separate papers twice, and they're not there, that just didn't make sense to me. So let's talk about that. There's two of them out there that are commonly referred, and in my book, I just repeated the company line that, yeah, we can't find them, the coordinates are wrong, you made a mistake, or whatever. But let's look carefully at that now that we're familiar with what the sky plates look like. So let's talk about SH214. So this shows you the red plate. Now, by the way, the blue plates aren't in existence, or I can't find them, they don't show up in the database. So, but that's okay, we don't need the blue plates. So SH214 is the center of this plate. And believe me, I looked all around this center, blew it up, looked at it all different ways. Let me show you the inverse of it. This is the inverse of it. There is nothing there. You know, it's like, what are you thinking, Dr. Sharpless? There's nothing there. And I was really pulling my hair out, what's left of it, trying to figure out what he was thinking. I was even messing around with switching the signs on the galactic coordinates. Maybe he screwed up that somehow. And I did think about this in passing. So if you look not that far away, there's this big star cluster there, bright star cluster. And I'll show you what it looks like in a real photo in a second. But I dismissed that immediately because it's a star cluster. I mean, it's a globular cluster. So those are spherical. Those are round. I mean, you're obviously not gonna. And actually, he did not label it as a round shape. So I thought, I immediately said, it can't be that. But it's really interesting when you zoom in and look at that globular star cluster. It does not have a circular shape, and I'm not exactly sure how or why it shows up like this on the sky plate. That's the way it looks in real life, but I would have thought that a cluster like that would show up on the sky plate as a sphere, but it doesn't. And so then I did a little bit more research, and it turns out, and by the way, this is comparing. So if you look at the image we just looked at here, which is the actual globular cluster, and then you compare it to, let's say, an HI image of an object the same size. This is very small. And that's the key thing about this lost object. It's only 2 arc minutes in diameter. It's very small. So it's got to be something small and bright. And you say, well, it can't be the cluster because it's round. Well, it's not round. And not only that, but if you zoom in here, I'm not going to zoom in, but it looks actually pretty much like this one here, which is SH242. So the signature that it has on the plate is actually very similar to a small H2 object. So I looked a little bit more into this. Sure enough, there's a star cluster here. It's called ESO 45511, which is also called HP1. And it was actually discovered in 1954, which is a year after Dr. Sharpless's paper was issued. So at the time he was doing this work, it was not known to be a star cluster. This shows you my image of it, and you can see how this looks like a small star cluster. But it actually has the same diameter, form, structure, and brightness as Dr. Sharpless said for SH214, so it makes perfect sense that it would be that object. And then after I came to all this, I separately discovered last week that there's a footnote in a 1973 paper by Pavla Marslakova, 1973, and that's a really good paper. It's called A Comparison Catalog of H2 Regions. And in the footnote, he said SH214 is this star cluster. Now, I don't know how that got lost over the years. People haven't latched on. I've never seen that. So, I mean, we can debate that all day long, but I'm convinced that it's not a missing object anymore. I think SH214 is the star cluster. The question is, how did he get it 18 arc minutes off? That's not a trivial amount, but I don't know the answer to that. So now with the time I have left, let me go down to the more interesting missing object, and that is SH2195. And before I do that, I want to talk about something called transients, which I'm sure a lot of you are somewhat familiar with. This has become a hot topic lately. So transients are when scientists here in the last 5 years have been studying these POS1 plates that you're looking at and finding objects that show up in those plates that were not seen before that plate was taken and have not been seen since that plate was taken. And an example of that is shown here. This is from a 2023 paper called A Bright Triple Transient That Vanished Within 50 Minutes. So the left side is showing the POS1 plate, an inverted view of it. And one thing I want to say up front here is when we talk about these transients, these are tiny, tiny dots that look like small stars. And so what you're seeing here on the POS1 image is a tiny triple star system that's at the center of that red dot. And these are the same size plates. So I zoomed in on this. This is actually a zoomed in version of this plate. And on the right side, you can see there's nothing there. This is a PAS-2 plate that was taken in 1990. So the second revision of PAS was done from sometime in the late 80s to early 90s. So this, I'm saying 1990, it might have been a year or two before or after, but regardless, it does not show up on that plate. So something showed up on this 50-minute exposure that's a triple star system that is not there right now. And so these transients, like I said in the bottom, are tiny star-like dots that are seen on the PAS-1 images, but not before that and not after. They've actually checked other PAS-1 images and found where there's overlap. I don't know if this was one of the overlaps, but where there's some overlap, they've actually checked those transients and they don't show up. So that they were only there within that 50-minute window of the exposure of the plate. So the question is, where do these transients come from? And that's where a number of these papers that have been issued in the last 5 years have been addressing. So let me just go through this now. They've actually identified 100,000 plus of these transients on these PAS-1 plates the past 5 years. When we talk about these plates, I mentioned this in the past, these are actually copies of the original plates, which to my knowledge, nobody has actually looked at since they were originally taken, and now they're archived. So these are copy images. You need to keep that in mind. The papers conclude that possible causes here are transients caused by the nuclear testing, which was going on at that time. They don't know how it could contaminate it that well in this manner, because they actually kind of do look, if you zoom in, they kind of do look like stars. Now, one of the papers says that these transients look like they were only visible maybe for a few seconds, because they don't have much in the way of if you study all the other stars, you can see a little bit of tracking there over the 50 minutes, a little bit of blurriness, but you can't see any of this blurriness. And so they've done a lot of analysis, and they've concluded that if these are real things, they were only there for a few seconds. So the papers think the causes could be nuclear testing or what they call identified phenomena, and it's like UFOs showing up, like our comet here recently. So those are possible causes that the papers come up with. The papers eliminate what you call natural causes, like gravitational lensing, gamma ray bursts, fragmenting asteroids, plate defects. They're all said to be unlikely. Now, more recent work concludes that these transients could be what they call emulsion holes on the plates that were used when they were copying the original PAS-1 plates. There's also some theories out there that it could be just contamination due to, there's an example out there where some plates over in Europe were contaminated with matches that they were using in the observatory at the time. Or there's possibility of humidity contaminated, or people that have sneezing, just droplets or something contaminated that way. So right now, for these tiny starlight transients, there is no solution. There is nobody that has come up with an answer to this. And I like what this one paper has said in 2020. It said the mystery of the transients is a detective story worth the attention of the astronomical community. So that's all fine and good. You're saying, Gary, what does that have to do with the missing object? Well, I'm here to tell you that I think SH2-195 is a transient. And I've never seen that published anywhere. I've never seen anybody talk about it in that manner. But let's look at the plate. So at the start of the presentation, I showed you this, if you remember. This was the plates I showed you for SH2-197. And if anybody is paying really sharp attention when I was showing these plates the first time, you can go back on the recording and look at it again. You will see SH2-197s here, but you will also see something here that is, I don't know exactly how far, maybe 14 minutes to the right of 197. And of course, nothing shows up on the blue plate. Well, if you look at the coordinates from the Sharpless catalog, SH2-195 is where this object is shown on the PAS-1 plate. It's not missing by any means. Dr. Sharpless saw it here and recorded it here. The issue, though, is that, and this is what it looks like up close. So this is not a transient like we just saw. The other transients were dots, tiny dots, that looked sort of like stars, but I would say, it's easier to get your head around that that's some kind of contamination, especially when there's 100,000 of them. This is the only transient that I've ever seen that looks like a nebula. What I'm talking about, to be clear, is this dark area that's in the center here. So that dark area, oops, I didn't mean to do that. So this dark area that I'm showing here, it shows up on the PAS-1 plate in 1951. There is absolutely nothing there in 1990 on the same PAS plate. And when I took the image of this area, there's absolutely nothing there. So like I say here, whatever this object was, it was visible in 1951. It was actually in the original paper that Dr. Sharpless put together, not SH2. It was in the SH1 paper. It was also in SH2, but I think he first saw it early on. But it hasn't been visible since. So what's unique about this transient compared to the other ones you saw? I've talked about this already. It's a diffuse transient. It's not a small star-like one. It's large, relatively speaking, in terms of how many arc minutes it is. It's not a tiny dot. It's an established catalog object. It's been around, since 1951, and it was captured early on film in the PAS-1 surveys. So most of the nuclear testing did not occur until later in the 50s. So to say this is due to nuclear testing in the atmosphere, this doesn't make sense. So this is my last slide. I mean, what caused the transient? So it's a non-stellar, diffuse, non-symmetric shape that's unlike any transient I've seen. Now, it'd be logical for other transients to show up. I don't know why there'd only be one transient out there, but I don't know if anybody's ever looked at the PAS plates to try to figure that out. It's not that simple to find these diffuse objects. It takes a little bit of work. The unusual shape and brightness profile, which to me it's not a round shape. It's got a very diffuse, smooth profile. To me, it eliminates anything like a supernova or a nova or something that's star-based. And I don't think it could be gravitational lensing or gamma ray bursts or asteroids or anything like that. To be honest, and then whatever it was, whatever they took a picture of, it's unlikely to dissipate completely in 30 years. At least, I don't know of anything really that dissipates that quickly over time. I mean, supernova remnants kind of expand, but you're talking about something that goes from being visible on a plate to being completely, you can't see it. And even on my plate, which I stretched the heck out of, I couldn't see any sign of it on there. So I can't think of any likely possibility that could have caused this transient on the PAS-1 plate. And, I come back to this, what they had said about the other transient. It is kind of a detective story, and it would be interesting to study this a bit further. So I'm going to show it to you again. This is what it looks like close up. So the conclusion here is, I don't think either object is missing. I think that first object, SH214, was actually the globular cluster, and there was just a mistake in the location. The second one, though, wasn't Dr. Sharpless's mistake. He actually saw something on that plate that we don't see today. And what it was is a real mystery. So my hour is kind of up, so I just want to stop right now and say I'm happy to take any questions.
Gary, I have a question.
Go ahead, Eric.
Did either one of Sharpless's children go into astronomy?
I don't think so, because, well, if they did, it was a very low profile. Yeah, that's a good question. You'd think there'd be, odds are that they would want to follow his father's footsteps. But I'm not sure of Astro. It's not like being a football player or musician. I don't know if people would at that time they're becoming more popular now, but we're still pretty nerdy. I don't know if people aspire to be like us.
Well, I just wondered whether there's if you contacted them, they could give you any background about some of the questions.
Yeah,
like, why does he have no profile online?
Yeah, I don't know. Yeah, I don't know. Yeah, that's a good question.
Eli wants to know what your next imaging challenge is.
Well, there's a guitar behind me, so I picked up playing guitar in a band here for my church, and that's been a big challenge for me. So I really don't know. I've kind of run out of catalogs. I've looked at some of the other catalogs, and like, I'm not going to do all the NGC catalog. I'm not going to do IC. it's got to be something that piques my interest.
Yeah, yeah. Yeah.
Because that's the good stuff in those.
You know, there's other catalogs out there, but
if
I don't know.
anybody is going to do it, it's going to be you.
Gary, you can stop presenting if you want.
Oh, okay, great. Thank you.
You know, the shape of that kind of reminds me of Hubble's variable nebula.
Ah.
I wonder, I mean, how what's the deepest exposure you've seen of that area?
Not very deep. That's a great question. I should just image, 100 hours on it with my RASA, and if there's something there, it would come up for sure. Because when I did that galaxy, it was my typical 5 hours with f7, and that's not going to get you a whole lot. But having said that, the PAS2 plate did not show anything, and that was with a 48-inch scope for an hour. So those PAS images were able to extract a surprisingly amount of signal. But it's great. It's a great point, Molly. I should go back, and I will actually, because it's easy for me to do, and just see if I can see anything else there, especially with my RASA. I'm really intrigued. I don't know if this is a real object or not. I really don't know, and I don't know if it's a real object. I don't know what it could be, and if it's not a real object, I don't know what it could be. Because if you look at the signature, it's very like when I've seen the flaws on the plates, and you can actually see some of them when you look at that close up. They're very distinct, and I just don't think it's like what I would call a flaw. Maybe it was a reflection of some sort. I don't know.
My other thought was just like some kind of smudge. I mean, I have not done any like physical image, chemical development kind of stuff, so I don't know what kinds of things can go wrong with that. But I wonder. I'm sure somebody has ruled that out.
Yeah. Well, no. If you look at the blue, for some reason, I don't know what's the emulsion process, but if you look at some of the blue plates, I do see some smudges on there. The problem is those are pretty obviously smudges. This one just looks very similar to SH2 195. It's nice that 195 is so close to it because you can do a comparison side by side, and it actually looks very similar in profile.
Wonder if it's possible that the star that was ionizing it is no longer putting out enough energy to do that.
I think that's a good possibility, but would that actually happen over just 50 years of time? I don't know.
Yeah, but by the size of it, how many light years do you think that thing stretched? How big was that object?
Yeah, so it was actually, if you look at the distance that's supposed to be when at least for 197, it's not that far away. I don't remember how many million light years, like 10 million light years. So it's a close galaxy. And I would say it would stretch maybe for 10 or 15,000 light years, something like that.
Well, okay. Then if the ionization stopped, if whatever was illuminating it stopped, how long would it take for the illumination itself to stop?
Yeah. And it doesn't have to be
15,000.
Yeah.
That's going to be a nebula as opposed to a galaxy, right? Given its shape.
Well, that's what I was going to say. We don't know what type of object it is. It could, based on what I've seen on these plates, that sort of signature pattern could be something else too. I don't know, some kind of molecular cloud or something. I don't know.
I think the big sneeze explanation is probably the easiest. What's the principle? The simplest.
Keep it simple, stupid.
Yeah.
No.
Occam's razor.
Occam's razor. Someone sneezed.
Well, the sneezes, from what I've looked at, when they've done that analysis, it's more like droplets. It's not. It's not sort of smooth, diffuse pattern.
Well, that's why I said a big sneeze.
And what bothers me a little bit is that there's been so many hours put into looking at these tiny transients, these dots, that they just aren't as interesting to me as something that would be diffuse like that. Because I think something diffuse has got a more likelihood of possibly being something that's real,
But why people are spending so much time looking at these transients when it seems, I don't want to say obvious, that they're flaws of some sort or another.
No, the one scientist has studied it for 5 years, and he keeps putting paper after paper out that insists it's not a flaw. And so I guess it depends. I mean, it's like the alien comet. It depends who's looking at it and what their passion is and the angle, the glasses they're looking at it through, I guess. I don't know.
So we're not going to go with aliens with a big vacuum cleaner sucking up the
I
nebula.
actually thought it could be exhaust from an alien spaceship. Just it's probably some disturbance or something.
It's the scoop for the fuel.
Yeah, the ramjet.
Like that comet that's coming after us. That comet that's coming after us and sending radio signals.
Yeah.
You know, there was
gravity.
a lot of pollen from the trees in the area. I mean, let's look at the
What's
simplest
weird, whatever it
explanation.
is, why doesn't it show up more than once on 2,000 plates? Now, I haven't checked every plate, but I did look at quite a few. I never saw anything like this. And why wouldn't it show up in one of the other 313 that he picked? You know, it is weird.
Yeah.
There is one other question in the chat, which is, when do you sleep?
Well, in all seriousness, you know, you can set up these scopes to run through the night. I think all of you know that, but I don't do that. So because I'll wake up every hour, at least hour and a half, because nothing makes me mad when I get up in the morning and I find out it got, you know, clouds went by and it somehow got stuck and didn't restart. So I do take short naps, but I just can't. And that's really, frankly, that's one of the reasons why I backed off a little bit lately, because I do feel like, you know, the more research they do on your health and your brain, sleep is supposed to have, you know, a lot of impact, positive and negative, with how you do, especially as you get older. So I'm trying to be more careful about that. I would just say that.
You know, I think that's a great argument when you tell your wife you need to buy some additional automation.
Gary,
My wife is the most understanding wife in the world. She's put up with me for and my hobby for a long time. So.
Barry, Logan says his dad is about to finish the Sharpless Catalog too. What should we
know.
look at next?
I know. Logan, I want to say hi to Logan. You know, he's one of the best young astronomers that we have out there. And yeah, his dad's almost done with that catalog. What was there a question there? I'm sorry.
What should he look at? What catalog should he pick up next?
Oh, man.
ARP or regular galaxies?
Well, I don't know if he's done Caldwell. Caldwell's actually fun to get through, and he could do that, but he may have done that already. ARP was, you know, ARP was a journey. That was, and I may actually do ARP again. That I can never get enough of ARP. You know, like nebula are okay, but
yeah, but
the stars.
I don't think, you know, a lot of the ARP galaxies are really, really small. They're just not pretty pictures. Yeah. I mean, it's like you can check that off, but you didn't enjoy it.
Yeah.
I would say after they've got the Messiers and the Caldwells, okay, the Sharpless is probably the prettiest catalog, I think.
Well, VDB was fun for me too. VDB was fun, but there are some small ones in there as well. I think every catalog.
Barnard's, the Dark Nebula.
Well, and that's, if I was going to pick one, that would be the most likely one for me, because I've already got most of them, you know, so I could do that. But there's a lot in there that are like, eh. But it could be, if I get enough signal, though, it could be they could start to get more interesting.
Yeah.
What do you think about the hydrogen beta contribution to H2 areas? I mean, if you got hydrogen alpha, you got hydrogen beta, and that's blue. And so the assignment of that to be red may not be accurate.
Yeah.
Well, a lot of hydrogen regions, the stars that power those are not quite hot enough for hydrogen beta in a lot of places. And so you will just see the red signal. And
a lot of them are. So when I assign that color, I add about a third blue to those areas.
Well, it's interesting you say that, Eric. I used to do that as a matter of routine, just always assign some of it to the blue. I kind of got out of that habit. I don't know why I got out of it. I just got out of it.
I think it's a reasonable assumption.
Yeah.
Since we really don't know for sure, but
I think what I saw, at least on a few images, is I get the most kind of contrast and the most definition when I have the most separation of those signals. So I don't know. The color may not be quite right, but the definition maybe is a little better. I don't know. Anything else out there?
I don't see anything.
I think we got all the
Alex?
I was hoping somebody would solve my problem for me. I'm not going to say I lose sleep over it, but I kind of do. I really would like to figure out what's going on with this thing. I feel like Dr. Sharpless is a little bit restless as well. So yeah.
Was he aware of this issue?
No. This is the first time it's ever been talked about in public, to my knowledge.
Actually, we've got some new questions came in. And from Tarek wants to know, he wants to have Gary tell us about your 356 clear sky location, please. 356. Maybe he meant 365.
Yeah, I've had a number of people, a lot of my friends that are probably out there watching, threaten to move in my empty lot next door. Yeah, so it's interesting. So I live on a big lake, second biggest lake in Texas, and the lake creates its own weather. So when it's warm, like it is now, the shores will heat up faster than the lake. The lake's a big heat sink. And as the air rises on the shores, it sucks all the moisture out of the middle of the lake. And so many times we'll have clear skies over the lake and clouds all around the lake. In fact, I've got these satellite views that I showed that during my compendium talk. It clears the skies out for me. So we do have some really nice skies here. And I do think the lake actually helps, even though humidity's high, it makes it very stable because I don't have any obstructions. That wind is just coming slowly across that lake, and by the time it hits me, it's very laminar in terms of the flow. So my seeing is typically really good, and I have no clouds. So yeah, maybe the community here should market itself as an imaging place. I don't know, but they definitely don't have the light pollution thing down though, because every new gas station and restaurant and everything that goes up is just lit up like a Christmas tree. So. But right now, they haven't figured out a way to put lights on the lake, so I'm still doing pretty good. It's for those of you that are interested, it's Bortle 4.5 about, which isn't too bad as close as I am to civilization here.
Do you get any light from Houston, or is that too far away?
It's it's an hour and a half away. I don't know if it's 65 miles. Yeah, we do get that light. So if I'm getting imaging down on the southern horizon to within like say 10 degrees, it does affect me there. But the problem, the atmosphere is so wonky at that level anyway that I'm not going to get a lot of good things there. I've gone down to 6 degrees before, headed that way, but that's mainly just for star clusters. That was to get my last Caldwell object, Caldwell 85.
Okay.
All right. Anything else pop in? I don't think so. Several thank yous. Another Starfront person, woohoo. Yeah. Okay.
Well, thank you. I mean,
it's
always an honor to present it to people that appreciate. We've got a weird hobby. Most people, my neighbors and friends and relatives, it's sometimes hard to have these conversations with. So it's it's fun to be able to talk to people that can understand and appreciate the work. So thank you for that as well.
Yeah.
Yeah, we always love having you on. You always have really interesting talks, and I think any of us who have used the M Compendium in this room, I'm sure, love the M Compendium, and I've used the heck out of it. That's for sure.
Thanks, Mike.
And yeah, you have done a service to this community in putting that together, plus all of the catalog imaging you've done. So definitely keep that up.
And when we end the show, you're welcome to stay on for a little bit.
I'll stay up.
Yeah, you can stay on and chit chat. Alrighty. Yeah, like and subscribe so that more people can see our stuff. And if you have a topic idea that you've thought of during this talk or any other time, hit that contact us button on our website, theastroimagingchannel.org. It's also where you can find our calendar of upcoming talks. I'm trying to be more on top of posting to the Facebook page, but sometimes I forget. And then, of course, YouTube will tell you our upcoming shows as well when I get those posted. So, yeah. And thanks for coming on, and we'll see you in a couple weeks. Good night, all.
Bye.
Bye-bye, everybody.
Bye-bye.
Have a good
See you
night,
in a
you
couple
all.
weeks.